Okay, I just wanted to make a quick video for section 6.4 in your book, which is just another application of the trigonometric functions and equations that we've been working with. And it's actually one that we have done in some respects earlier in the semester. We can now just kind of manipulate it a little bit. And the idea is, well, suppose we have a weight hanging from a spring. So suppose I have a little spring right here, and then at the end of that spring, I have a little weight. And now suppose that I take that weight and I kind of release it and let it go. Well, suppose, say, I've got it stretched out a little bit. I mean, that's kind of what it looks like right here. What is the spring going to actually do once I release it? And we can kind of draw several pictures to see what the spring's doing over time. And essentially, if I've pulled this down and released it, well then when I release it, it's going to start going up. And then it'll maybe keep going up until it hits some maximum point. And then once the spring hits its maximum point, it'll start going back down. And it'll keep on going until the spring gets nice and stretched out. And when the spring gets as stretched out as it's going to get, well then it'll start going back up again. And now essentially we have a bunch of pictures of what the spring is doing over time. And what we can do is, well, kind of connect the dots. If I start right here, what does this weight on the spring do? Well, it goes up, and then it goes down, and then it goes back up, and then ultimately if I kept on going, it'll go back down. And essentially we have a trig function there. That looks pretty much like a sine wave, up to my ability to draw reasonably straight. Which essentially means if we want to look at the motion of a spring, we can use our trig functions, our sine waves, our cosine waves, things like that. Essentially, it's just a couple of equations that we need to work with that are similar to ones we've worked with before. One thing to keep in mind, in the real world, if I did this, if I pulled this spring down a little bit and released it, it would go up and down and up and down, and eventually it would stop. It would kind of go up and down and up and down, and eventually the spring would give out and there would be friction and stuff, and it would kind of settle in on its equilibrium point right around here. For the purposes of this, we are not going to do that. There's two different types of spring equations, motion of a spring. Right here, if we neglect friction and assume it will just continue going forever, we get what's called simple harmonic motion. The other case, which is the more realistic case in the real world, where friction takes over and ultimately the spring slows down and reaches equilibrium, that's actually called damped harmonic motion, because there's a dampening effect. Okay. For the purposes of this class, we're really only going to care about simple harmonic motion. The damped harmonic motion is similar, but the equations are a little bit more complex and they're not really necessary for this class. I may give you a homework problem just to mess around with the damped harmonic motion, but we're really only focusing on the simple harmonic motion. Essentially the idea, just really quickly, if we say had a spring similar to the one up top and I released it but friction took over, then it would go up and down, but then it would kind of keep getting smaller and smaller and smaller and settle in on equilibrium. And essentially I have a sine wave or a cosine wave, this is the sine wave, that gets smaller and smaller and smaller and closes in on equilibrium. The equations are slightly different and slightly more complex than the simple harmonic motion ones, so we're not really going to worry about them. But as far as it goes for simple harmonic motion, there are two standard equations. I want to use the letters your book uses, so D equals A sine omega t. Or D equals A cosine omega t. Both of those equations describe harmonic motion. We'll talk about the letters in a second and what they mean. But first off, the big key point that tends to confuse people, if you're looking at a spring problem and you're trying to figure out which equation to use, which equation do you use? And essentially it boils down to thinking about the spring you're talking about and seeing what it's doing. Meaning, for the one we just drew, we said we pulled it down a little and then released it, so it went up and down and up and down and up and down. It started in the middle, right here. Sine waves start in the middle, which means to describe this motion, we would use this equation. If, on the other hand, we say, took a spring, and we had attached to, say, the ceiling, and we put a weight on the end of the spring and kind of held it right against the ceiling, and then released it, what would happen? This is the ceiling up here. The weight would start right here. It would go down, and then all the way back up, and then down, and all the way back up. And now my wave is starting at the top at its maximum. That's a cosine wave. So ultimately, it doesn't actually matter which one you use. You can manipulate these things, but it gets really complex. So to make it really easy on yourself, think about the spring, the whatever it is you're talking about. We'll have different examples on your homework. And decide, is it starting at its maximum, or is it starting at equilibrium in the middle? Think about the graph and what's going to go on, and that will indicate to you which equation you should use. So now, suppose we're using this equation. We have that A right there. This W right here, it's not actually a W, it's an omega, it's a Greek letter, but that's omega. Suppose we have the equation D equals 2 sine of 3t. Suppose that is the model for my spring that I'm working on. Well, yes, this is the simple harmonic motion equation, but it's no different than the sine waves we've been dealing with. When we dealt with them before, when we first defined these, what did we care about? Well, we cared about the constant out in front. When we did it before, we said that was the amplitude. It was amplitude before, this is still a sine wave, it's the amplitude here. Meaning the spring goes up 2 and down 2, just like a regular sine wave. Inside here, we said this 3 right here, our omega, when you multiply something times t or x inside the sine, well, that just changes your period. And we said the trick before was, to find your period, you would do the original period of the sine wave, 2 pi, and divide by 3. And that's it. That tells me that this sine wave has a period of 2 pi over 3, or if we're talking about a spring, the period of the spring is 2 pi over 3. So we're not doing anything different here. We're doing the same trick we did before with the same sine or cosine waves, the same A, the same constant here. They mean the same thing. We can just maybe use different words for them because we're talking about it in the context of a spring. But don't think it's somehow something new when it's not. The only thing that really is new is when we have springs, we have what's called frequency. Frequency is essentially how many times it completes a cycle in a unit amount of time. If that's a little bit confusing, don't get lost in all the physics-y type terminology and all that, and your book lists a lot of it out. Don't get lost in it. All you have to do is take your period. Whatever your period is, to get the frequency, you just take the reciprocal. So if the period is 2 pi over 3, the frequency is 3 over 2 pi. And that's it, you're done. As far as it goes, that's it. It's pretty straightforward. Maybe to quickly do one example so we can see it in practice. Let's see, suppose I have a spring. It starts at equilibrium. It has an amplitude of 4 and a period of 10 seconds. Come up with an equation that models that and figure out the frequency. Well, let's see. It's starting at equilibrium, which means it's starting in the middle and it's going to go up and down and up and down. Since it starts at equilibrium, it's going to be a sine wave. So we'll say D equals A sine omega t. And now let's see. Well, A is my amplitude. The amplitude is 4, so I can just replace A with 4. No big deal. Now I have to figure out what omega is, what this constant is right here. Well, let's see. I need a period of 10 seconds. And ultimately, how do I use this omega? We said whatever omega is, you do 2 pi divided by omega, and that will equal your period. Well, my period is 10 seconds, so make the period 10. Now, just algebraically solve for omega. So let's see, multiply the omega over, and you'll get 2 pi equals 10 omega. Divide the 10. Omega equals 2 pi over 10, which reduces to pi over 5. And now there we go. We know what omega is. We can plug it in right here. So, replace omega with pi over 5, t. And now, there's my equation. Starts at equilibrium because it's a sine wave. That tells me the amplitude is 4, which is what I want. The period, if you want to check it to make sure your algebra is correct, once you get this answer, just go through the problem again. We said the rule was to get your period, you do 2 pi divided by that, which is pi over 5. Do the math. Here, the 2 pi's will cancel. We're dividing by a fraction, so this 5 gets multiplied on top, and we get 2 times 5, which is 10, which is the period I want. So there we go. This equation works. The last thing I suppose we care about is finding our frequency. But we said the frequency was 10 seconds. I'm sorry, the period is 10 seconds. The frequency, just take the reciprocal, 1/10. And again, I would point out this one somewhat different than the last one. The pi can confuse people. The period is 10 seconds, which means it completes one period, one wave in 10 seconds. The frequency, like I said, in terms of the physics, is how many cycles, how many waves you complete in 1 unit of time, or in this case, 1 second. Well, logically, if it takes 10 seconds to complete one wave, we complete 1/10 of a wave in 1 second. So the frequency makes sense there. If it's confusing with the pi, just remember, take the reciprocal. But when you drop the pi and just have numbers, the idea of the relationship between the period and the frequency makes more sense. So think about it that way. As far as it goes, that's pretty much it for these springs and their equations. Like I said, we're mostly going to focus on simple harmonic motion, and I'll give you some homework on it to mess around with it. But be aware, both on Alex and in your homework, there may be 1 or 2 problems with damped harmonic motion. It's not the biggest deal, not something we're really focused on in this class, but it can be fun to mess around with. So I might give you some homework on it just to mess around with it a little bit to see how it works. If you have any questions, feel free to stop by my office or email me like normal.